And this is led by, oops, what happened?
Can you share screen again? The recording has started, so.
Ah, I see. We also have simulation technology to accelerate the high-performance computing simulation by using AI. And by collecting data from this deep search and simulation technology, we will train a generative model which can generate or design new material structures satisfying specific target materials properties. And we have finally we have a lab automation system which can automatically identify and predict the required chemical synthetic paths to synthesize some specific target molecule. So by repeating this cycle, collecting data and carrying out simulation and training our generative AI to design new material structure and tested it on the robotic lab. By repeating this cycle, we expect to accelerate the speed of material discovery. But on top of these our existing rather historical or even conventional accelerated discovery technologies. In the past a few years, we launched a new initiative. It is foundation model for materials. Let's say multi-modal foundation model for materials. And that is the core topic of today's our seminar. So what is a foundation model for materials and why do we need it? So today we have a bunch of AI technologies in predictive or generative modeling, but these technologies or AI models are isolated or siloed in terms of the training data or material domain or applicable uh, uh, target functions. For example, someone may create one model which is pre-trained with smiles strings extracted from, for example, drug data. But this model will be used only for generating new molecule. Another researcher would create another model which is pre-trained with molecular graph data extracted from another material domain, which can be used only for predicting binding affinity with specific target protein. And some other researchers create another model like this, but each model are fully decoupled together. And that's why overall we are uh, struggling with some limitations in terms of model scale and data sample size. Most of these models have small parameter size, less than million order, and each model can be pre-trained with trained with only small amount of data because researcher can collect only limited data. And most of the model can handle only single or two data modalities in maximum. So these models are often suffering from accuracy in terms of property prediction or reliability in the sense of generation. And of course, many researchers over the world create similar models again and again over the world. So a lot of redundant efforts are happening over the world. So on that background, we are building a more centralized large model, which we call foundation model together. So we are building a large foundation model which has a larger parameter size on the order of billions of parameter size, pre-trained with massive data sets. Uh, the number will be even more than billion samples collected from many material domains like a semiconductor, drug, or photoresist, or OLED material domain with multimodal data sets, including smiles, graph, or even molecular images, electron density images, etc. So such a large model is pre-trained with massive data uh, to capture the foundational knowledge about material structures. So once the foundation model is pre-trained with such massive data, the model can be adapted to wide variety of downstream application tasks. So by attaching downstream head to the foundation model, um, a user can use that model for property prediction of some specific material domain only by additional extra training with a small amount of data. One model can be applied to generation of new molecules or predicting a reaction pathway or materials, other characters like optical absorption, emission spectrum, etc. So the important key point of this foundation model is multimodality. So as you know very well, the material can be represented by many modalities. For example, small molecule can be represented by, for example, smiles, a representation. But of course, the molecule can be represented by many other data modalities, including molecular graph or fingerprint, optical spectrum, or list of the basic property, 3D atom positions, or images of electron density, energy diagram, or even text description you can find on Wikipedia can be one of the representation of the molecule. So by gathering, in another word, fusing this data modality or feature representations into a single feature representation, we can create a robust, more robust and rich feature representation to represent the molecule, which can be used for downstream predictive or classification tasks with high accuracy and reliable fidelity. And also in the training phase, by capturing the relationship between modality like atom and fingerprint, smiles and basic properties, you can use the foundation model to translate one modality to another modality in a similar manner as Japanese to English, English to Spanish, Spanish to Japanese again. For example, inputting smiles, the smiles representation can be translated to a list of basic properties. And this is equal to property prediction from a specific molecular structure, or vice versa. By inputting a list of basic properties list, this can be translated into the list of the candidate smiles, equal to generating brand new molecular structure starting with required properties list. One even more complex task, like inputting basic properties list with optical absorption spectrum. This can be translated to candidate or smiles, equal to discovering or inverse designing new molecular structure satisfying target basic properties and absorption spectrum. So we are going to provide these functions not only by web API, but with natural language based, uh, like a conversational user interface. Inputting query like generate new molecular structure having the following properties and emission spectrum with its chemical synthetic path. And the system gives answer with in the same manner as you communicate with a human chemist uh, in a daily conversation. Okay, so this is a very, very high level overview of our work. So let me a little more dig into a little more detail about models and algorithms. So I have only maybe 10 minutes, 10 more minutes, so I'll quickly go through. So our overall architecture is rather than pre-training a single large model from scratch, we adapt a more flexible and extensible architecture, late fusion scheme. It means First, we pre-train each modality-specific model by each independent data modality. For example, one transformer model is pre-trained with the smiles, and another model is pre-trained with selfies data in a self-supervised manner. And like this, now you prepare other models. Each of them are pre-trained with each individual modality-specific data, like molecular graphs, 3D atom positions, electron densities, etc. Once, once you prepare such a pre-trained set of pre-trained models, you can fuse these models. You can fuse each feature representations in a post hoc manner by fusion algorithms like a mixture of experts, dynamic fusion, LLM fusion, etc. Like this. And after fusing to a single model, you can apply these models to downstream tasks. You can use this fused model for some specific property prediction like glass transition temperature or peak absorption wavelength prediction. Or, as I mentioned before, you can carry out a modality to modality translation, like smiles to properties, or text to smiles, or property to smiles, etc. So, now let me very quickly introduce what kind of modality-specific models we have in IBM, developed in IBM research. So, okay, for example, we have SMILES model. This is one of the model we are going to introduce at the demonstration today. Here, the encoder-decoder architecture of transformer is pre-trained with SMILES collected from PubChem dataset and created specific for this purpose. And another model is selfies model. Actually, this was developed by Indra sitting here. The BART transformer was pre-trained with a list of selfies retrieved from Zinc and the PubChem dataset. Here, 1 billion samples are used for pre-training the model. And the third model is, this is also will be used for today's demonstration, molecular graph model. Here, the encoder is, for encoder, we are using a graph neural network. And for decoder, we are using our invention, molecular hypergraph grammar decoder, which always generate valid molecular structure. So this is also used for today's demonstration. And we also have other modality-specific models. 3D atom positions model, which has a transformer architecture pre-trained with a small molecular data set, and also periodic materials, including metal organic framework like this. This also gives a very strong feature representations on the latent space. And we also have a 3D electron densities specific model. Here, in this model, the electron densities are 3D grid image, and the SMILES representations are, let's say, aligned on the latent space in the same manner as a CLIP model does. And we in IBM Research Tokyo, we have another model, topological distance descriptor model. This is a kind of chemical descriptor rather than model. This is a new descriptor invented by us, which the descriptor which captures the distance between specific substructures like this and this, or this and this. This descriptor creates a list of the intramolecular substructure distances and create a sequence of descriptors. And we also have a spectrum model and a text-based model where text to molecule or molecule to text are carried out on the by combination of the transformers. So like this, we have a bunch of multi-specific models already pre-trained, and we are going to fuse some of these models to create a multimodal foundation model. Today, we are developing just a naive concatenation, mixture of experts, LLM fusion, dynamic fusions. But for today, let me introduce only concatenation and mixture of experts. So the first example is just a concatenation. Let's say this is not algorithm.
Seiji,
Yes.
can I interrupt you for a second before we go to the next to this new chapter? Because there is a question
Yes.
in the chat. I don't know if you can answer.
Yes.
It's about the graph, the molecular graph model, and it asks, does the decoder in the molecular graph model also revert the node aggregation operator?
Decoders, what operator did you say?
I'm not sure if it makes sense, but it says.
Does the decoder in the molecular graph model also revert the node aggregation operator?
Node aggregation operator. Sorry, I'm not sure about what is a node aggregation operator, but this is basically a algorithm to automatically kind of let's say assemble the molecular fragments to create a molecular graph structure from encoded latent vector. So the graph information is encoded to a feature representation by graph neural network. But from starting with that information, this molecular hypergraph grammar assemble a molecular concrete structure by attaching fragments and atoms and even some bonding informations. So we have a NeurIPS workshop paper. This was presented in NeurIPS last week. Actually, you can find the link here. So if you're interested in, you can go to that. Indra-san, could you
share the link?
Share the link on the chat. Okay, thank you. So I try to finish my talk within hopefully 5 minutes. So, but if you have any other questions here, I can pause.
Let me elaborate. The molecular graph encoder probably has a node aggregator at the end of the extract embedding. Does the decoder take the embedding and construct a graph with nodes? Molecular graph encoder probably has a node aggregator operator at the end to extract the embeddings. Does the decoder take the embeddings and construct a graph with the nodes? Okay, from the embedding, it does try to reconstruct the molecular graph. But more than reconstructing the molecular graph, what it tries to do is MHG, the hypergraph grammar rule, it tries to apply the grammar rules, and then the output is actually a string representation rather than a graph representation. Does that answer your question? I think his question is, does it reconstruct the
yes,
graph
basically
itself?
basically the model is pre-trained to reconstruct the original input molecule. So okay, so this might be not answering to your question, but the molecular hypergraph grammar has a very strong advantage to always robustly reconstruct a concrete molecular structure, satisfying molecular rules. So as you know, in sometimes SMILES decoder or selfies decoder decodes some molecular structure which is cannot exist in terms of molecular rules. But this decoder always robustly create molecular structures. So leveraging this character, we are pre-training GNN part and this RNN part to in a self-supervised manner. Okay. So let me go to the next fusion algorithm part. And actually, the first one is rather than a fusion algorithm, this is just a naive concatenation of each feature representation obtained for each respective modality, SMILE, self-fit, molecular graph. Each feature representations are simply concatenated on the fused latent space, and this is given to the downstream predictive or classification model. Here, for example, predictive model to predict some target properties given in the benchmark dataset MoleculeNet. So here we have some comparison of a single modality case and multimodal case. And we tested each model's performance with respect to each target classification and property, not prediction, but classification tasks. And higher score is better. And as you see, sometimes some multimodal cases, like a SMILE self-is graph case, is the best, for example, for HIV classification task. But sometimes SMILES and graph is the best. But for some tasks, even single modality gives the best performance. So like this, still we cannot clearly prospect what combination of modalities would be the best and what uh, we cannot say the best combination of the multimodalities. And in addition to simple concatenation, some of the Brazil teams are working on mixture of experts to fuse different modalities for the same tasks. So here, the mixture of experts algorithm dynamically select appropriate combination of the modalities depending on the downstream property prediction tasks. Here also, we did the same comparison on the same target properties. But as you can see, some of the properties here and here, mixture of experts work best on HIV classification comparing to concatenation. But for some other properties, the simple concatenation is best. For example, CleanTox, simple concatenation works best. So like this, what kind of lesson we can learn from here is depending on the target properties, we have to carefully select the right combination of the modalities and the right fusion algorithms, concatenation or mixture of experts, or even dynamic fusion or LLM fusion. Okay. So we are not presenting today, but we have other fusion algorithms like a dynamic fusion or LLM fusion, which will be presented in another opportunity. And we also have some cross-modal inferences like SMILES to property or property to SMILES. So like this, we have by aligning the each modality's feature representations on the common latent space, we can carry out the selfies to list of DFT properties and the UV absorption spectrum, or vice versa. DFT properties to selfies in the spectrum, or spectrum to selfies and DFT properties. And for this kind of tasks, we can improve the algorithm by optimizing the latent space sampling scheme. For example, some folks in UK team is working on GFlowNet, which optimizes the latent space sampling scheme leveraging the GFlowNet. And this work has been already published on some of the papers like Digital Discovery and URIP's workshop, etc. So you can also go to the reference if you're interested in. Okay, so these models has been already applied to many use cases like battery or semiconductor material domain. Actually, Indra worked together with Almaden research, IBM research, Almaden researchers to apply the model to batteries prediction. Can you very shortly
Oh, we will be having a hands-on session
Oh,
with the battery.
you have that today? Oh, great. So this battery example is something you can try at the hands-on. Great, thanks. And we also exploring domain application in semiconductor area and also carbon capturing material, including metal organic complex, sorry, a metal organic framework, and also polymer film to block CO2 gases. And some life cycle material design. And okay, these model functions are consumed with a chat interface, as I introduced at the beginning of my presentation. Some researchers in Almaden Research Lab are working on development of LLM-based agentic workflow. Here, the LLM-based agent understands user's query and identified what kind of model should be, what kind of APIs or which model should be called to answer to a user's query, and automatically creates a workflow of the API and carry on the run the workflow to answer to the user's query. So you can consume such a model's function via this kind of chat-like multimodal user interface. And finally, let me very briefly introduce about the AI Alliance. As some of you may have heard of AI Alliance. This is an AI-related consortium which was built just 1 year ago together by Meta and IBM. So this is a consortium in which people work together to build a transparent and reliable AI, real open AI, not open AI, but open and transparent and reliable AI together with all member companies. So I think today we already have even more than 100 member companies and institutes and some academic universities over the world. And in the AI Alliance, we have several working groups. And just a half a year ago, we launched new working group for materials and chemistry. So the purpose of this working group is to gather AI skills, knowledges, and materials knowledges, and work together to build a foundation model which can be consumed by anyone over the world, and create sharing data and creating a benchmark and sharing knowledges about material domains and work together to build our best and biggest foundation model for materials. So in this AI Alliance Materials Working Group, we are organizing several events. For example, the first event was a technical kickoff workshop held in Tokyo in last May, and some social gathering event was organized at ICML workshop in Vienna. And I forgot including here, but okay, I will prepare, and at the end of this seminar, I will introduce in Europe this year at Vancouver, we will also organize another social event where we introduce about our overall activity together with some other research consortium like Acceleration Consortium in Canada. Okay, so like this, with organizing these events and seminar and technical meeting with a lot of material companies, more than 20 material companies and academic institutes are joining this activity. And we are building a foundation model. So recently we released 3 foundation models from ourselves. It means we carved out 3 core models: SMILES model, selfies model, and molecular graph model as a kind of seed models for this activity through GitHub and Hugging Face. So starting with these 3 seed models, we are now build many companies and institutes started contributing to this activity to make it more and more valuable and useful for actual use cases in material domains. So I really hope some of you also join this sizzling moment. Okay, so this is summary, but yeah. As I mentioned, we are developing multimodal foundation models, and we are carving out some of our foundation models as a seed model for this kind of open development activity. And today, Indra is going to give a demonstration and hands-on of these 3 modality-specific models. Okay, that's all from my end. Thank you very much for listening to my poor English lecture. Thank you very much.
Thank you, everyone. Does anyone have any questions at this stage? Maybe before we move on to the hands-on, if we had a quick couple of questions, we can take them now.
There's one question in the chat. Are these cross-validation results example from K-fold CV?
K-fold CV?
Cross-validation, these are actually just train and test values. These are not K-fold results, but in some of the papers, we have also tried with different seed values and provided the mean and standard deviations. But the link that I shared, the paper, that is not K-fold validated, I guess.
Any other questions or yeah? Okay. So if you don't have any other extra questions, maybe we can hand it over to Indra.
Yes. So okay.
There
so
is
let's
one
move
more
on to...
question in the chat. Which kind of actual activity is organized in the worldwide collaboration workshop data sharing?
Yes, what we are working on today is, okay, we are providing 3 modality-specific models: SMILES, selfies, molecular graph, and now some of the companies are using our model by their own company's proprietary data and sharing the results and feedback on the technical meeting with us. With us means not only IBM, but also other joining companies and universities members. And we discussed there what kind of extra improvement will be required to make the model more beneficial for all of us. And also, sometimes we share part of the data here And also, yeah, we are creating a common benchmarks. But yeah, creating common benchmark and sharing data set is how to say, yeah, sharing data, but creating benchmark is coming work actually. So sharing model and sharing a feedback and sharing the results and the feedback and sharing some of the data. These are, and also we are now creating a new framework of working together towards some specific publications on some specific material domains having a common interest across the members.
Okay, sorry, I mean AI Alliance and Working Group for Materials.
Yeah.
Okay. So any other questions? Okay, so moving on to the hands-on part, I've posted a couple of links that we'll be using today. So the first link is the GitHub material. Let me quickly share my screen. So in the next 1 hour, we'll be having a set of hands-on demo of these 3 models, the SMITED model, which is a selfies-based model, smiles-based model, selfies-TED, which is a selfies-based model, and a graph model, MHE-GED. So today we have 2 types of demo that we can run hands-on. One is on Jupyter Notebook that you can run on Colab. So as long as you have a Google account, we will be able to access the files from there. And the second one is through a web UI. So those who are not very comfortable with programming, we could still experiment with these models on the Hugging Face space. The kind of material that we've prepared today is 2 data set based. One is on the molecule net, which is a standard benchmark that is used. And the second one is an example of an industry application or how we can use it for specific use case applications such as battery electrolyte. Now, irrespective of these notebooks or the Hugging Face spaces being shown only on these 2 examples, you can always try it on your own custom data set. So we will go through that as well. So moving on to my screen. So this one is the GitHub source code page. So this is our GitHub source code where we have all our models that are open sourced. Please take a look at it. You can always git clone, fork it, or we'll be really happy if you could start it right away.
So please click start now. It's just a joke, but
because this is completely open sourced, at any point in time, if you feel you would like to contribute to this project or join us in contributing to the FM4M activities, please raise pull request, add your own features and create a pull request, and we can work together on merging it together. So this one I would like to show you is using the web GUI. So this is hosted on Hugging Face. I have posted 2 links, FM4M Demo 1 and Demo 2. So I think we are about 40 plus people on this call, and all 40 of us accessing the same Hugging Face may load the server and it might be too slow. So I would request half to try on one of the Hugging Face spaces and the other to try on the demo space too. Of course, I have no way of dividing who accesses which one, but if you find one server being very slow, please feel free to jump to the other one. On my side, I will show it on local and you can follow the same. So we have 3 parts in the radio demo, the web user demo. So the first one is data and model setting. So we have an option to select from built-in data set or load your own custom data set. So let me first show you with a built-in data set. So these two examples are from the MoleculeNet data set, which is a standard benchmark. Base is a classification problem. It is what beta, some Secretary's classification problem. So currently we have the following models that are available: selfie-STED, MHG, Molforma, SMITED, and these two are standard baselines that you can use for comparison. So first, let me show you the single modality case. So in the model, I'm going to select selfie-STED. Since this data set is a classification problem, I choose task type as classification. You can choose the downstream model from this list. I will start with the default so that I don't have to set any hyperparameters, and I will train the model. So currently what is happening in the downstream task is the default model is loaded with the embeddings obtained from selfie-STED model, and it is trained. And since it's a classification problem, the metric that is used for evaluating it is the ROC-AUC score. We can also visualize certain features. For example, we can visualize the ROC curve and also the latent space distribution of this particular data set. And say if we want to store this result, we can click on store log, and it would update the table for you to compare results later. So if I want to change it to, say, MHG GED and do the same thing, I would train the model again. So this one gave me a slightly higher score. Now, what happens if I combine these two models? So I'm selecting both selfie-STED and MHG. So this is a multimodal example. And currently, we have only the naive concatenation type of fusion. So I'm going to select on that and train the model. So this would take a couple of minutes because it's fetching both the representations and then fusing it. And we have the ROC score. So if we look at our table, we can see that selfie-STED was 85, 0.85, MHG was 0.869, and combining these two models increased the score to 0.871. So similarly, we can combine any number of models and train our downstream task. Now, because I selected 4 models, this would considerably take a little longer time because it has to fetch the embeddings for each of these models. But then we have the score. So this is an example where we can see that combining all 4 models does not necessarily improve the score. So there is a particular combination in which the models can be actually contributing towards improving the score. So these are some aspects that we are still researching on. Now let's take a look at a classification example. I will start again with, say, one model. This is a regression problem. And this time, let me choose a simple regressor. You can choose the kernel, you can choose the degree, you can adjust the hyperparameters. Once you've set the hyperparameters, click on Create Model. So this is the parameter with which the downstream model is being trained. And let's train our model. Now, because this is a regression problem, we can see the parity plot. So our RMSE score is 0.53, and this is our latent space. Now combining 2 models together, I forgot the previous score though, and I forgot to save it, but then I think it was 0.5 something, and this reduced the score to 0.41. So this is a simple GUI where you can experiment with our models, do simple hyperparameter tuning with some of the existing models that are defined over here, and visualize the results and compare the model's performance on your own data set. Now for custom data set, what we could do is you can choose your CSV file. So many files. You choose your train data set and your test data set. Now you get a small preview of the CSV file that you just loaded. You have to select what are your input columns and which one is your output column. So here my input column is smiles and my output column is property. And say I try it with Molforma. This is again a regression problem, and I will go ahead with the default settings. So this would take a couple of seconds for it to read your data set, get the respective embeddings, and then get you the score. But this is the result. So once you store it, you can use it for your comparisons. Now the third column is molecule generation. So what this basically does is you can give an input reference molecule, and given the initial reference molecule, it would search the latent space and try and generate a molecule that has higher QED score and lower SA score. So I'm selecting from examples. There are 5 predefined examples that you can choose from, or you could also type in your own smile string. Benzene, yeah. So here first, I will go with a predefined example. This would take roughly about half a minute because it would first get the embedding for this particular molecule and then perform small perturbations around the latent space and find a molecule that has higher QED and lower synthetic accessibility. So over here, we have the property of the generated molecule. So if we compare the reference molecule and the generated molecule, this particular substructure has been replaced, I guess. Okay, this particular substructure. There's a double bond here, but here it's replaced by a nitrogen atom. And these are the properties. So the reference molecule's QED score was 0.496, and the generated molecule's QED score was 0.60. And it also shows the similarities, the Tanimoto similarity between the generated and the reference molecule, and here it is 0.78. So this example, the list of sample examples over here are designed to improve the QED score. You could always try any random smile string and then try and generate. So you can keep clicking on generate to see if you're able to generate a molecule that has higher QED score or lower SA or one of the desired properties from this list. So far, any questions or any difficulties in the WebUI based demo?
Hi, Indra. I think you have some comments on the chat.
Okay, my experience with some MoleculeNet benchmark is that the data set can be quite small, which leads to observation that k-fold cross-validation shows much less variance than repeated train test. Yes, that is true. That is true. So, like I mentioned earlier, when we report the results, we haven't really tried k-fold cross-validation. So we just do repeated random seed values and then present the variance results. But I agree with the comment. Does it show the parity for a single test set? So this parity plot is for the test data set. So you have the train and the test set. So depending on what is the size of your test set, it shows all the molecules of in the test set. So has anyone tried the Gradio app, the Hugging Face demo? Anyone has any issues or comments on the interface? So the web UI is basically
Until when can we access the demo page?
Oh, the demo page is already publicly available, so you can access it throughout. Both all the links that I have shared above, these are already open sourced and they're always available. So we have tried to keep the Hugging Face space in such a way that you don't have to worry about coding or working on the intricate functions that actually run this code, but with simple button clicks and UI options, you can still evaluate these models on your custom data set or the built-in data sets. So for people who are more interested into diving deep on the back end of all these functions and would like to have more experience on coding it, we have also prepared a couple of collab notebooks, basically two of them, one showing the functions that you see on this web interface, and the other one is on a particular battery use case example. So I will quickly first run through both the examples, and then maybe we can have the last half an hour for you to try hands-on and then discuss if you have any issues or any errors that you're stuck with. We can also divide into breakout rooms and handle into smaller groups. So this one I would like to start with is the battery example. So before I explain what exactly is happening here, let me go ahead and clone the GitHub repository and install some of the packages that are necessary to run this particular code. So the example described in this particular notebook is from our paper that was presented at ICML this year at the ML for LMS workshop. So here, in case of battery electrolytes, it's actually a mixture where you have multiple constituent components that are mixed in a particular composition ratio. So here, what we try to do is create a representation for that mixture model. So let me go ahead and import the required libraries. So once I have my cloned repository, so this is exactly my GitHub page. All the files and all the code that is on my GitHub is now cloned onto my Collab server. The dataset is located under dataset/LSC. Both the train and test datasets are provided. This is a very small dataset with only 151 electrolyte formulations. If we take a look at the dataset, it has 6 constituents. SMILES strings are the constituents corresponding SMILES representations. And the concentration columns represent the concentration in which that particular constituent is mixed. So the idea behind creating the representation for the entire mixture is that for each of the SMILES string, we pass it through our encoder model. In this case, we're using the selfies model and get its corresponding molecular representations. So once we have the representations, we try and scale them to the corresponding composition ratios and then add them. So the effective feature vector or representation that you get is the representation of the electrolyte mixture itself. So going into the code, so all the related functions that you would require for evaluating our models are provided inside this FM4M package, which we imported in the beginning. So if we want to have a look at what are the available models, we have SMITED, SelfieSted, Molforma, MHG, and 2 of the baseline models. So this is the same as what we saw in our web UI. For this case, let's start with, say, the selfies model. So I would first get, so if we follow this diagram, for each of these SMILES string in my battery example, I would get their corresponding molecular representations. And the model that I'm using over here is the SelfieSted model.
By the way, TED stands for Transformer Encoder Decoder.
So this is a selfies-based transformer encoder decoder. And SMITED is SMILES-based transformer encoder decoder. And MHG is molecular hypergraph-based graph encoder decoder model. This is taking some time, but the get representation function, the input would be your train SMILES list, your test SMILES list, and the model that you would like to use to get these representations. Now, in this case, I don't want it to return it as a tensor, so I've given it as false. Let's wait for a few more seconds. Okay, now we have both the representations ready. I'm just doing some data cleanup by dropping out any null values in my data set. So once we've done that, we go ahead with our replacing our SMILE string with their corresponding representations. And for obtaining the feature vector of the entire electrolyte formulation, we now multiply or scale the embedding with their respective concentrations. So once we do this, we have our train and test data. And here I'm using an SVR regressor to compute the RMSE score. So we have our RMSE score as 0.276, which is actually a good score in terms of predicting the Coulombic efficiency of the formulation. So I think I've missed to say what we are trying to actually predict over here. So given this electrolyte composition, we would like to predict the Coulombic efficiency of that electrolyte mixture. So this is one example where we could adapt or use the FM4M package to train battery electrolytes or any particular use case applications. So if you have any use cases in mind and you would like to try the FM4M package, you could try it. So a quick break here. So far, does anyone have any questions? Or first of all, is everyone able to access the collab page? Is the notebook and the collab notebook and all the files that was shared accessible to everyone? Thank you. So we will come back to say a small breakout session where we can have and resolve any small issues that you might have in running these files. Moving on to the next example. So the FM4M example _ demo notebook is basically the source code or all the functions that you see in the web UI. This is an example of the same set of functions. So we again start with cloning our repositories and installing the required packages. Once we clone our repository and install the packages, we set the path. Now the FM4M package contains all the necessary functions to call all the models and the fusion methods and single model functions. So while it is importing, let's quickly revisit the FM4M architecture. So we have different modality-specific models that are pre-trained on their corresponding modality data sets. And using the representations of these different modality-specific foundation models, we can fuse them and use the fused representation on particular downstream tasks, such as property prediction or even molecule generation. Now, the workflow goes like this. We first load the data set and get the corresponding representations for the molecules in the data set using one of our foundation models. And using the latent representation, we fine-tune a downstream model in the downstream task. So this downstream task could be either property prediction or molecule penetration. So this notebook also contains examples on how you could use for visualization. In this case, we start with the ESOL data set, which is a regression problem. We load the data set. The data sets are present inside the data directory. So this is our data. We set the input and output fields. So our input is the smile string, and the output is the property column. So we've set them accordingly. And curate our xtrain, ytrain, xtest, and ytest. So these are our input and output labels for both train and test data set. So now that we've loaded our data set, let's go ahead with getting our representations. So the list of models that are available in the package are SMITED, Selfie-STED, Molpharma, MHG. Now we have the train test and the train and test data set. So we get the representation or using one of the models. So here the model that we're using is MHG-GED. So the syntax goes like this. So you have the train data set, test data set, the model type, and whether or not you want to return it as a tensor. So with MHG-GED, it would take a couple of seconds for it to get representation. Now we have the train and test representations. Now the dimensions for each of these models also varies. For example, SMITED, the latent representation dimension is 768. Selfie-STED is 1024. MHG-GED is also 1024. Now, the sample is we have 854 samples, and each of them are 1024. Each embedding or each latent representation is 1024. So this is the shape of our train and test data set. So now we have two examples. The first one is a single modality case, and the second one is the multi-modality case. So first, let's look into the single modality case. So in the single modality case, we have a function called single modal. So fm for m dot single modal, you can pass the model that you want to train upon. So here our model is MHG-GED. We pass the train feature or the embedding, the label, the test data, and the test label, and the kind of downstream model that you want to use. So similar to our web UI interface where you had different options to select downstream models, we also have a set of downstream models that you can select from. So here I've selected default regressor.
What's the default regressor?
The default regressor is actually SVR running in the background. If you select SVR, you could also feed in the hyperparameters. So here it's running with the default hyperparameters. And for default classification, it is actually the XGB classifier with the default parameter settings. So now we can see that the RMSE score is 0.4085 and it's generating some plots and it's done. So how we can use these results? So the first, so this result is actually 6 dimensions. So the first parameter would give you the RMSE score. The second one is actually the raw score. Okay, and the third, this one is for the parity plot, and the last two are for the latent space visualization. So I will show you how we could use it for visualization by jumping here. I did ROC. Okay, it's supposed to be parity plot. So parity plot should be this one. So this is a parity plot. Now we can repeat the same thing for multimodal case, that is when you select multiple models. So how we do that is fm4m.multimodal, and we pass the list of models that you want to use. So in this case, I want MHG and SMITED model to be evaluated. And I have my X-train, Y-train, X-test, and Y-test. And my downstream model is again a default regressor. So let's see if the multimodal case improves the RMSE score. So for the single model case, we had 0.4085. Okay, so our RMSE score is 0.4051, which slightly improved. So if we were to check the regression latent space, we could use the same functions. So if I want to visualize the MHG GED's latent space, I first get the representation, evaluate them, and visualize it. This is the parity plot. So you can redo the same example for any custom data. So if you were to try it for a custom data, make sure you upload the CSV file to the collab file, or if you're trying it on local, you can directly enter the complete path, and you can split the data set, or if you already have a train test split in place, you can just load the data set and use the same set of functions to evaluate the models. So this is from a code perspective. If anyone is interested in trying out these models, you could try it from code or using a simple web UI. So far, does anyone have any questions or any issues?
So at this moment, we haven't implemented any auto hyperparameter optimization or this kind of functions. But if you can try on Jupyter Notebook things, you can customize the script to fitting into your purpose, like combined with the existing hyperparameter optimization library or something others.
Yes. So in the papers that we have evaluated these models, we usually use Optina for hyperparametric tuning. You could also try hyperparameter tuning with Optina, or with some limited features, you can try tuning with these parameters.
Of course, for writing a paper, we are using hyperparameter tuning optimizer, but for this kind of experience version, we don't.
Yeah. So here we just have the default parameter settings. So if you still want to try with different parameters, you can either manually set them. So if you're on the code side, if you're planning to set them, you would be passing the hyperparameters as a dictionary similar to this.
On this dictionary. Yeah, you're right.
So does anyone have any questions or any issues with running any of the examples so far?
Actually improve performance a lot. Yeah.
Yes. So optimum hyperparameters would definitely improve the performance, but it doesn't mean that the default parameters of performance is bad. You could quickly try with the default parameters, and to further get better performances, you can try hyperparameter tuning.
So maybe we can pause here for 10 to 15 minutes and finally wrap up. Okay, so here maybe we can pause for 10 to 15 minutes and we can leave you to try by yourself. And after, yeah, let's say 15 minutes, we come back for wrap up the seminar. But of course, during these 10 to 15 minutes trial time, you can anytime ask questions on chat or yeah, anyway.
So has anyone had any issues with the collab notebooks so far? So while the others are trying out the examples, we just have a quick announcement that if anyone is attending NeurIPS, we have a NeurIPS socials that will be held on December 11th from 7:30 to 9:30 p.m. We also have an AI Alliance exclusive socials that will be held on December 13th. That is close to the NeurIPS venue. So if anyone is around at NeurIPS, please feel free to join us at the socials to discuss more. We also have a couple of poster presentations and papers related to this current work, and also other fusion strategies like mixture of experts. So we could also have some discussions at NeurIPS or even later. Does anyone have any questions, any comments or feedback on, or if anyone is interested in contributing to FM4M, any suggestions, any comments? So this is our social event. If you're attending NeurIPS, please feel free to join us at the socials. There is a small RSVP page. please sign up and let us know that you're coming.
We can say
Okay, we have a question. ESOL dataset that I work with has 1128 molecules. Were some molecules discarded? On canonization of these 1128 molecules, I think some of them were invalid. That's why I think it is 800 samples. In case of smile string, there could, okay, so one of the reasons why we had selfies based model is because selfies make sure that the molecule is always valid. But in case of smiles, it does not guarantee the syntactic validity. So in case of some brackets missing or an extra slash or an extra symbol, it does not actually guarantee the validity of the molecules. So that's why usually one way to clean up is using the rdkit sanitize function or to canonicalize the molecules before using them. So some of these molecules in ESOL dataset are dropped out because of that. They could not be canonicalized using the rdkit library. I normally have no problem processing ESOL molecules with RT-Kit, but maybe you're processing using different steps. Okay, so the kind of processing that we did was basically canonicalize it and use the selfies library or the selfies package to get the selfies molecules. So you can pip install selfies and try if these molecules can be converted into selfie strings or not. So for the process, for it to be converted into selfie string, it needs to be first canonicalized or checked if the smile string is valid. If the smile string is not valid, it will not be able to encode it into the selfie string. I've also sent, okay, I haven't used selfies so far. I'll try that. Sure. So we have just created a brief feedback form. Please feel free to give us your feedback, comments, and how you found today's session through the form. Maybe Marco can also pass the feedback form to the other attendees who have already logged off. Yeah.
Yeah.
And all the relevant papers and related papers to the models, any upcoming news events are all posted on our GitHub page. All the materials related to today's session is also available through that GitHub page.
Okay. Thank you very much, Indra-san. And yeah, now we have 20 minutes left, but maybe it will be a good time for wrapping up this session today. So thank you very much for spending time and paying a lot of attention on our introduction and demonstration, and thank you for working on the hands-on session together with us. So now I would like to wrap up this seminar with some events, announcements of the events coming. So as Indra already introduced you, we are going to have a social event at the NeurIPS 2024, which will be held in December. Oh, this will be
it's actually December 11th.
Yeah.
So yeah, depending on which time zone you are in.
Yeah, this is Vancouver time. Yeah.
December 11th from 7:30 to 7:30 to 9:30 p.m. Vancouver time.
So yes, 7. And if some of you join the NeurIPS, please feel free to register the form. So the event page, the link to the event page is posted on the GitHub, so you can find it. And also, we are planning other demonstration and hands-on events for the next year for MRS Spring Forum and also IEEE next year. So by that time, I expect the FM forum, Open FM forum will be more enriched with some extra models, including fusion, new fusion models like dynamic fusion and some other algorithms. So I hope you'll be able to enjoy our extra functions on the new coming releases. And finally, some of the functions of FM4M is already implemented to some chat-like user interface designer, which was created by researchers of Acceleration Consortium and the University of Toronto of Alan Nussberg's group. So as you know that you may know, Designer is a chat-based interface to work with inverse design of molecular structure. So FM4M is going to be a part of the Designer function. So like this, I really recommend you if you to implement recommend you to implement the FM4M like this. If you find our function can be useful for your own material discovery process or your own material discovery platform like Designer. And as Indra already posted on the chat, we really appreciate if you could give us feedback and comments or questions on the questionnaire form. Okay.
Or even if you're interested in joining us or contributing to the project, you can reach us through the form.
Yes. So we are any new contributions or collaboration are very welcome. Okay. So if we do not have any extra questions or comments or suggestions or feedback, we would like to wrap up the seminar here. Anything else to add, Marco?
Marco, over to you.
Yes, thank you very much, both to the speakers and to the people in the room. I don't have much to add. I'm looking forward to stay connected with your group, but also with the AI Alliance. And well, I can make a small announcement about ChemAI because we already set a date for 2025, which is funny. It still needs to take place tomorrow, but we are sold out. I'm sure it's going to be a success. And save the date for the conference on the 21st of November, 2025. We'll be back, with great speakers again, and hopefully even a bigger conference with more topics. AI and materials is one. There will be AI and drug discovery, all kind of applications with the AI that involves molecules or lab automation. So yeah, follow us on LinkedIn to stay connected.
Okay,
Thanks.
you. Thank you very much, Michael, and thank you very much.
And also thank you to Hamada-san, Lisa Hamada, who's on call. She has been supporting us with all the operations so that today we could have a hands-on demo that is running smooth.
Thank you very much.
Thank you. Thank you very much.
Thank you.
Have a
Thank you
good
very
day
much.
and good weekend.
You too. Bye.
Thank you. Bye-bye.